Thank you.
They were able to hear them, I guess. It should work now. So testing with this chair's mic online. Can you hear the chair's mic?
Yes, we do.
Was that a yes? Yes. Okay. Okay, I guess speak up.
All right, attempt number 2001. So, very quick updates on documents. We have quite a few documents in flight. We have one document in that will be going to ISG review, which is hash to curve. I think the most interesting is probably next slides about various adoption calls we have. Madsen CFRG deterministic signature with noise document was very interesting to watch on the mailing list because of IPR concerns, even though the IPR is expired. Chairs are consulting with IETF chair to decide what the best way forward is on this. They seem to be interested in the topic, but a lot of people said that they want to work on the document conditionally. So this is, I'm not entirely sure how to, as a chair, how to process this information. We also have another document, Aegis in adoption call. There were very few comments until recently. There was some support this week. I think we're extending last call a little bit more to get more information about this. So if you have an opinion whether this should be worked on in CFRG, please comment on the mailing list. And with this, let's start with other presentations. I did sort of skip through it.
Okay, so right, here's our first presentation. It's about the Bbs Signature Scheme. We're obviously very tight on time here, so we'll sort of limit the questions and have the conversation, bring it online. But here is our presenter.
This one?
Yep,
So
the
okay.
slides are here.
And sorry, there's some transition, so will I just ask?
Just say next slide.
Okay, thank you.
The only difficulty is they cannot see you at the moment. But.
Right, okay, that's right. Hi all, my name's Tobias and I'm here to talk today about a signature scheme called the Bbs Signature Scan. So next slide, please. So at a high level, what are Bbs signatures with a few words? Effectively, it's a digital scheme supporting, next, there's a couple of transitions. Selective disclosure or multi-message signing, we call it. Next one.
You can also see down there.
Thank you. Thank you. Proof of possession enabled. And finally, unlinkable proofs through a zero knowledge proof protocol. Next slide. So just a bit of a timeline around where some of this work has originated from. The first appearance of this short group signature was documented in 2004, which is where the name BBS is derived from, the work of Bonnet, Boyan, and Shickham. There was been multiple revisions in academia since then, in a paper in 2006 and again in 2016. And then as a working group at the Decentralized Identity Foundation, we started work on documenting the scheme at the Applied Crypto Working Group in 2021. Next slide. So at a high level of the scheme, next slide, it is pairing based, so it uses type 3 pairings, 2 subgroups, G1 and G2 of known prime order. In the current cipher suite that's defined in the specification today, the scheme itself is curve agnostic, but the cipher suite we've defined within the scheme today in the spec is based on using the BLS 12381 curve, but as we said, any pairing friendly curve is compatible, provided it's type 3 in nature. Next slide. So there's obviously a problem with this slide, but effectively at a high level in terms of concepts, there are 3 parties involved in this protocol: signer, prover, and verifier, and there are 2 kind of core constructs, which are signatures and proofs. So if we move on to the next slide. The highest level summary of how this protocol works is a signer signs a set of messages and headers. Messages and headers are the 2 kind of application level payload kind of classes of application level payloads we can sign with the scheme. Loosely, a header is information that must always be revealed in any proof generated under this protocol. And messages, it's a set of messages. It can be n number of messages chosen by the signer, and those are selectively disclosable by the prover. A signature is generated over top of them, and then on the proving half of the protocol, prover can create a presentation header, selectively disclose, create a proof, and send that to the verifier for verification. Next slide. So just moving into the lower level sort of properties of how sign works, as I said on the last slide, there are essentially 2 levels of application level payloads here. The header, which is effectively a message or a payload that's always disclosed in any proofs generated, and the messages are selectively disclosable. The sign operation is effectively the signer that takes all of that information together, signs that, and produces a signature. Some notable properties is the signature is constant size, even under n number of messages, and that signature is essentially a combination of a single EC point and 2 scalars. In the context of the BLS 12381 cipher suite, that is 112 bytes in size. The slide has cut off on the efficiency. We were trying to say that it's O of n efficiency, or constant time if no selective disclosure messages are used in terms of the efficiency of the sign operation. And another thing that to note is in the scheme, you can either sign just a header or just a set of messages, or both. So the scheme's flexible in that regard. Next slide, please. So verification. This is a operation that would primarily be done by a prover, because the signature itself would never be revealed to a verifier directly. That's what proofs are for. But effectively, to verify a signature, it behaves much like a normal digital signature. You take all the information protected by the signature, which is the n number of messages in the header, and the signature, the signer's public key, and you get a result around whether or not the signature is valid. Again, that's ON efficiency, or constant time if no selective disclosure messages are used. Next slide, please. So the proof protocol is effectively the prover receives a signature with a set of messages and a header, and then they decide which messages they would like to selectively reveal if they are present in the signature. They produce a presentation header, which can be used to put in a nonce or scope the proof to a particular domain or audience. Combine that with the signer's public key and generate a proof. So the size of the proof is linear to the number of hidden messages. There's an equation there that gives you an idea of how that scales. Again, this operation is ON efficient, or constant time if no selective disclosure messages are used. And there's obviously a choice for the prover to make around which messages to disclose. Lastly, next slide, please. So BBS, the verify proof. So this is the operation that's performed by a verifier. They receive essentially the set of revealed messages and header. the presentation header and proof. They combine this information with the signer's public key, and that produces a result of whether or not the proof is valid or not. Again, ON efficient or constant time if no selected disclosure messages are used. Next. So the proof, just a note on what the proof provides, it proves integrity and authenticity of the revealed messages, also the header, and it proves possession of the signature. The presentation header is essentially bound to the proof as well, and the proof is said to be unlinkable because effectively the proof is it's generated under a non-interactive zero-knowledge proof protocol. Next slide. So these are some benchmarks for our implementation that we have most recently done for the most recent draft. We are still refining some of these, but this gives an idea of the characteristics that we've found. So the benchmarks, you've got a logarithmic scale on the bottom there. So this really shows that performance scales linearly to the number of messages. In the smallest case, where you are maybe just signing a header, you're not using the selected disclosure feature afforded by the Bbs signature, you're looking at a sign verify times of sub half a millisecond. And obviously the proofs, just for note on these benchmarks, as they go up, were generated where 50% of the messages were disclosed in the generated proofs. And there's some details on the machine those benchmarks are run on. Next slide, please. So just a brief section on some of the use cases we see for this scheme. The first is privacy preserving anonymous credentials. So effectively the ability to leverage the selected disclosure feature to produce attribute-based credentials that include personal information about someone, where they can derive proofs of the subset of that information signed by the original issuer to different relying parties, free from the risk of correlating themselves in presentations, and also providing the ability for them to granularly manage what information they share to different relying parties. Next slide. Another application is what we call proof of possession enabled security or access tokens. So this is what we believe is a feature that allows you to, say, issue a security token or an access token under a protocol like OAuth2, where the signer can just produce a access token secured with a Bbs signature, and then the prover, using the proving half of the protocol, can generate a unique proof and send that to, say, a resource server in a protocol like OAuth2, proving possession of that token, which is obviously an enhancement in terms of replay attack detection for a resource server over, say, bearer tokens. And there's also some simplifications versus other proof of possession enabled schemes that require the prover or the client to manage key material and prove possession of that and get that essentially tied into the token to do something. So that's one application. And then finally, the last one is essentially non-correlating security token proofs. So the idea that a signer can issue a single token to a client, and that client can then generate n number of proofs for n number of parties, proving whatever the presence of that, essentially what that token underlies, what that actually proves or grants the client, to different servers without being correlated through the cryptographic layer, say a fixed signature, because again, the proofs are indistinguishable from random. And just a quick note there, the indistinguishable from random is it's not an artifact of the presentation header, which is set by the client, it's actually built into the protocol. So just a quick note on why we believe, why we're presenting this work to the CFRG and why we'd like to continue it at the CFRG. We think it fits with numerous existing work items already here, which is notably the pairing friendly curves draft, which includes the definition of the curve that we're using present in the current CIFAR suite we've defined, which is BLS 12381. It also bears a lot of a relationship and structure and nature to the existing BLS signatures draft, and we also make heavy use of hash to curve in our draft. Next slide, please. So effectively, we'd like to call for adoption of this draft, And, we believe that it's sufficiently just evolved today to describe the scheme. However, it's, incomplete. As a draft, we've got numerous issues still in our repository, such as, we would appreciate a broader review of the scheme. The cipher suite kind of definition that we have within the spec today, which allows kind of extensibility in future cipher suites to be defined. We still have a series of refinements to do there. And then beyond that, also clarify some of the extensibility points that we have built into the scheme. A slide, please.
Quick question.
Yeah.
Is there any IETF work that will be using this?
Any what, sorry?
Any IETF work that will be using?
Yeah, so this afternoon there is a BOF, a Birds of a Feather session for a new, a call for what's called JSON Web Proofs, which proposes to essentially extend the Jose family of cryptographic data representation formats to allow and accommodate schemes like BBS. So yes, related work at IETF.
Chris Wood also wanted to comment, this has potential implications or applications to privacy pass as well. So there's another one.
Yeah. Thanks. I've definitely seen that work and I think that's fantastic. And there's definitely intersect and overlap with applications like privacy pass. So in conclusion, essentially it's BBS is an efficient multi-message digital signature scheme supporting selective disclosure and zero knowledge proofs. It's had quite a long line of research backing it up, improving its security properties and efficiency. There's been multiple iterations in academia over the years as well. We believe there are multiple use cases for which BBS can be applied. The current cipher suite's based on the BLS 12381 curve. Obviously, there's already work going on at the IETF, at the CFRG using that curve as well. Any pairing-friendly curve can be used. And we also believe that the signature scheme itself is also extendable to fit a range of other use cases. So that's it.
Okay, any more questions?
That's not exactly a question, but I'm very interested in seeing this work continue, especially in the context of securing cyber physical supply chains, given the performance and the size of the proofs. Thank you.
Yavnir from Dell. The verifier does need to have the public key of the signer, right?
The verifier does what, sorry?
Does it need to have the public key?
To verify the proof?
Yeah.
Yes.
Okay, so how is it unlinkable?
Sorry?
So how is it unlinkable? If you need to have your public key to verify your signature or the proof that you have signed something, how is it unlinkable to you?
Because the public key represents the public key of the issuer, so you've got herd privacy within, it's essentially a group signature. So if you say one issuer issues to a herd of, 10,000 or a million signatures, then any party that possesses a signature within that group has anonymity to that group.
Got it, thank you.
Okay, thanks. We're not going to do an adoption call here, but we'll definitely talk with the chairs and we'll decide whether to take it to the list.
Thank you.
Deirdre. All right, Deirdre.
Hello. There I am. Yes. Cool. Hi, I'm Deirdre. I work at the Zcash Foundation. This is Frost. Next slide, please. What is Frost? Frost is a flexible. Next. Next, please. Next, please. Round optimized. Next, please. This is 2 rounds for Frost. If you're familiar with any of the Frost work that has been published elsewhere, the thing that we're specifying in this document is the 2-round variant of Frost. That's where the flexible comes from. There were 2 variants. This is the 2-round variant. Next, please. Schnorr, next, please. Only Schnorr signatures or Schnorr-like signatures. There is no ECDSA in this protocol. Next, please. Threshold, next, please. I thought I would have a clicker. For every signature you create, you can use a threshold T of N possible signers, where those N possible signers have shares of the secret. Next, please. And that's the signature scene. And the resulting signature is indistinguishable from a single signer Schnorr signature, like an Ed DSA type signature. Next, please. So high level, you have already done some key gen, and then the document that we are proposing is the signing protocol after you've already done key gen. First round involves generating nonces, rather your contributions to the nonces, and then commitments to those and publishing them. And then the second round, you actually use those and all the other signing participants' commitments with your key share to generate your signature share. And then the coordinator, whoever that is, takes all these shares, signature shares, all these nonce commitments, and combines them together into the final signature, and outputs your Frost signature. Next, please. And next, one more. So this is a high level. Prior to starting the two-round protocol, you have done your key gen. Someone is operating as a coordinator. We've seen implementations where everyone can be the coordinator. In the thing we're describing, there is a coordinator. Next, please. As I described, you generate nonces, you create these commitments to your nonces, and you publish them in an authenticated channel, not a confidential channel, but an authenticated channel. Next, please. And then the coordinator or whoever who having distributed all the commitments to these nonces to all the parties who are signing, uses them to generate your signature share with those commitments and your signing share, your key share. Next, please. And then you send that signing share back to the coordinator, and you aggregate all those signing shares back into the final signature. Next, please. So, fully specified, we've been cranking on it for 8 months now. We have 4 cipher suites in the document: the Ristretto prime order group, P56, ED 25519, oops, can you go back? And ED 448. We have specifically specified these cipher suites and the API of the document to be compatible with ED 25519 and ED 448 verification. And we also have multiple interoperable implementations, several in Rust, at least one in C, our proof of concept or reference implementation in Python and Sage, over multiple cipher suites. Ristretto is popular, ED 25519 is very popular. Next, please. So some of the latest updates, there was a optimization that was proposed to Frost that would take order T scalar optimizations for if you have T signers in a single signing protocol, down to 1, order 1. And we updated the protocol, updated the specification to include this. But there was some further analysis that showed this introduced a inter-round malleability in the set of signers, not malleability of this resulting signature, but it wasn't clear that the people who started the signing in round 1 were provably the same set that finished in round 2. So we backed this out. We decided to eat the cost of the further scalar multiplications and just went back to the one where that was no longer an issue. So that is in the current version in V7 of the draft. And another big update is we were having trouble having a consistent subroutine definition of how to do verification for these signatures, because the ED 25519 document and other documents have led to their verification subroutine. They don't really have one. They have 2 lines of text. Suggest things that we would rather are musts, and they're sort of like, anyway, we have made this easier by having per cipher suite verification, which is basically the same operation you would do for singleton. So we're just trying to remain compatible while also like kind of giving strong recommendations of some of these cofactor curves of how we would like to see implementers implement verification. And then for general Schnorr signatures over prime order groups like Ristretto and like P56 that don't have an equivalent verification equation defined anywhere, we give if you have a prime order group, here's your verification procedure for a signature that uses a prime order group. So we include that. Next, please. So we think it's in a good place, and we're seeking crypto panel review and wider CFRG review. We've been cranking on this and talking to many people in the broader cryptographic community, but we think we are ready for the CFRG to really take a look at it now, because we've cranked on it a lot. Is there anything unclear in the draft? Is there anything ambiguous in the draft? Is there anything technically incorrect, insecure, or unsafe in the specification? Is it written in a way that embedding it into higher order application protocols or other things is clear and not full of friction? We always welcome more implementations. We haven't added it yet, but we're interested in adding another cipher suite over SecP 56K1, which is another prime order curve that we would like to see supported. That hasn't been done yet, but we'll see if anyone else is still interested. Next, please. And that's pretty much it. Do you have any questions?
Hi there, Daniel Kahn-Gilmore from the ACLU. Thanks for working on this. I'm wondering whether you think that we need to update 8032 because of the looseness of the 25519 signature verification. Like, do you see a path forward for that? Is that something that you would be interested in seeing happen? What are the roadblocks to that? I mean, this is not the only place where this has come up.
I would be very interested in seeing that happening. I don't know what the roadblocks are, but I will say that every implementation of ED 25519 worth its salt, and I've worked on a few, they're all doing the cofactor check, especially in places, as opposed to the cofactorless check, which is one is sufficient, not strictly required, and the one that actually multiplies by the cofactor is the one you need for example, consensus interoperability. And also, if you are using this where low order points or torsion points are an issue, which is a lot of places, you should just do the cofactor mul. And if the extra cost of that is an issue, I don't know what to tell you. Like you can run into serious security issues if you're not doing this cofactor check. I would highly like to see that document updated as an implementer and a person who does cryptography and that gets deployed in the real world.
Okay, one more question from inside the room, and then we have one from Meet Echo.
Great.
Mike Elmsworth. So I'm working on the composite, sort of combining PQ and classical together for security stuff within LAMPS. This seems like it's sort of solving a different application problem, but with the same technique. So I'd love to chat, see, make sure we're on the same page. Or
sure.
Yeah.
A lot of basic group assumptions, and the security proof reduces to one more Diffie-Hellman assumptions. So we can talk, but there are some security reductions that may not be available to PQ systems.
Okay, the question online is no longer here.
Okay.
So the queue is closed. All right, thanks, Deirdre.
Thanks. I'm here for today, and then I'll be leaving, so come find me.
All right, Chris Wood.
I'm going to do both of them. It doesn't matter which order. All right, so this is just an update on the key blinded for signature schemes draft that was recently adopted. Next slide, please. So just to remind folks what this draft is all about, imagine you did not have, or imagine the setting where you have what we call a prover and a verifier. Prover wants to sign some message and have the verifier check that this particular signature on this message is fine. Prover gets his input, a secret key and a public key and a message as well, does the signing thing, sends the message and the public key and the proof or the signature all the way over to the verifier, which just determines whether or not it's valid. And sort of obvious, we don't want the signature itself to be forgeable, so the prover can't trick the verifier into accepting this particular proof or this signature without actually like running the signing algorithm. Next slide, please. But there are other interesting applications wherein you might not want the verifier to learn anything else about the prover. Like you might not want the verifier to learn that this specific public key that this specific prover owned was used to verify this message. This has applications in Tor, this has applications in a variant of privacy pass, as well as other cryptocurrency settings, which we talk about. And I will describe in the next slide. So imagine you had a slightly different scenario where you have now two provers, each of which have their distinct sets of private and public key pairs. They're both signing a message. They run their signing algorithm independently, and they send them to some middleman or intermediary we call the mediator. Mediator chooses a bit at random and then sends the message, the public key corresponding to the bit, and the signature corresponding to the chosen bit to the verifier, and the verifier does the check as before. It wants to see if the signature over the message is valid, and it also wants to try to determine what was the bit that was chosen by the mediator. Next slide, please. So we have the same property as before. The signature itself is not forgeable, which is great. Next slide. But we don't have this other property of sort of unlinkability, wherein the verifier doesn't learn basically which prover generated this particular signature. Because the verifier is assumed to have as input the public keys corresponding to prover 0 and prover 1, and it can just simply check, does this validate with public key 0 or does this validate with public key 1? And that determines my bit. So that's the property we want. Next slide, please. And so this signing with key blinding extension of a digital signature scheme is basically how we go about constructing this. And it basically has two fundamental properties, the first of which is that the per message public keys that are produced are independently distributed from what we call the long-term public keys of a particular signer. So these PK0 and PK1 in the previous slide. And moreover, that the signatures that are produced don't leak any information about the long-term signing keys. And this is what this construction allows us to achieve. Next slide, please. So I said it was a sort of an extension of a basic digital signature scheme, and the extension basically adds in 3 new functions on top of your classical key generation, signing, and verifying. 3 of functions are a new function to generate a blind key gen, a function to blind a public key, and then a function to sign with a blinded key. And the correctness property that we want is sort of listed at the bottom, so you can run the verification algorithm over a blinded public key or against a blinded public key using the output of the blind key sign function with that same blinded key, and everything should work out just fine. The verifier is totally unaware that this particular procedure took place behind the scenes. It just knows that the signature is valid and was not forged, which is great. Next slide, please. There's also optionally the ability to add yet another function to this particular construction, the ability to unblind a public key. So if I give you a blinded public key as well as the blind key that was used to produce that blinded public key, you can invert the operation and recover the sort of the long-term or the input public key that was not blinded. So here you just, basically the inverse of one another. And I don't know what happened to me echo, but I'm just going to keep talking. And so the question for the draft specifically was, how do we achieve this sort of optionality in practice? Next slide, please. And so what we chose to do, the proposal that we came up with, was to sort of contextualize the blind public key function itself. So previously it just took as input a long-term public key, a fresh ephemeral blinding key, SKP, and that was it. It would just produce a blinded public key. But now we slot in this additional context string where context can be entirely application defined. So for example, in the privacy pass application, it's empty, it doesn't have any particular value, and that allows this unblinding operation to take place because the person who wants to unblind knows what context is, and they can do so. In the context of Tor, there's a slightly different construction for specifying what the context is. It includes the long-term public key and like a timestamp, or whatever. I forget exactly how it's encoded, but that's functionally what happens. And that sort of prevents this unblinding step from taking place because you don't know, as a verifier, either one of these, you don't know the long-term public key. The proposed change is up on a pull request. It's been reviewed by a couple people. It seems pretty straightforward and obvious, so we'll likely land that after we get some implementations and new test vectors going. Next slide, please. Okay, and then just to remind people about the implementation status, so we have implemented this for all of the signature schemes that are in the draft, both EDDSA and ECDSA, and there are different they're interoperable, these different implementations. We do have a security analysis of specifically the unlinkability and unforgeability of both EDDSA and ECDSA completed. It's under peer review right now, so not publicly available yet, but if we ask the right people, potentially we can make it available. Next steps for this are to hopefully merge the PR that I just talked about and then start soliciting early review, ideally from the crypto review panel, because at this point we think the document is feature complete. Next slide. I think that's it actually. Yeah, questions?
If there's queues open online. Anybody joining? It seems not. Thank you, Chris. Let's move on to the next presentation.
Hello?
Hello? Hi, Bjorn.
So finally, now I get home, I'm hearing a lot of at least I'm hearing you now. Could you show the slides?
Are we doing what, next presentation? Yeah, we're done.
Is it RSA or sequence?
Blind RSA.
Excuse me. I got wrong. I got it wrong. I'm too early.
Bjorn, Chris is going to do another one.
Bjorn, you are next after Chris. Chris will do another presentation.
There's one more presentation, Bjorn, and then we'll get to you. Okay, so this is a really quick update. Thankfully, in the interest of time, for a while now, we have the draft, this draft in the group on specifying blind signatures based on RSA that have been used in a huge number of applications. So it was about time we wrote down how to do this correctly. Next slide, please. Thankfully, we had someone in the community conduct a security review of the scheme in the paper. Unfortunately, however, it raised a number of concerns with the draft as specified that were not things that were considered in prior analysis of the construction. The main insight was that previously, when trying to reason about the blindness property of blind RSA, folks did not consider what happens if the signer's public key is generated maliciously, because you're trying to define blindness against this person who's verifying the public key, and if they construct this public key in a particular way, in a malicious way, information can leak when the client engages with the protocol, which is not great. And this is specifically, or especially problematic for the deterministic variants in the draft, specifically those that use the full domain hash for the actually encoding of a message, and any other sort of deterministic variant like PSS with a zero-length salt or whatever. It's important to know, though, this is only a problem with low entropy inputs. So if you are using blind RSA for a voting application where there's like 5 people or whatever in your pool, running a protocol with this type of input could leak your vote or bits of your vote. But if you have applications where you have a high entropy input like Privacy Pass that has a freshly chosen 32-byte nodes as input, it's not an issue. It's also worth noting that it's also not an issue if you have, for example, proof that the private or the public key was not chosen maliciously. You can in fact generate non-interactive zero-knowledge proofs that someone can check, specifically the client that wants to engage in this protocol, to see whether or not the public key was constructed correctly. But they are not standard, and they only give us sort of probabilistic guarantees that things are okay. So that said, next slide. A resolution to this issue and to deal with this emerging security analysis is basically to start stripping away things that we included for the purposes of having the draft be maximally useful for a number of applications. The first of which is we're going to remove all the deterministic variants from the draft and just sort of enforce or require that PSS with a salt length that matches that underlying hash digest is the way to go. Perhaps in the future, if there's some new insight that we get that allows us to bring this back or some of the deterministic variant back, we can do so in a separate draft. I don't think it needs to block this particular work. And we also added text to talk about what happens if you're an application that has low entropy inputs, specifically what you should do to add entropy to your input generated locally on the client. This is interesting because if there's randomness that's generated locally before invoking the signing protocol, that randomness has to be part of the message now that the verifiers will consume and verify. So it does have API implications if you're using the construction in that particular mode where you're generating local randomness or local entropy. But if you're an application like Privacy Pass that has high entropy inputs, you can use the scheme as it was previously before without any problems. Next slide, please. So at this point, before we actually merge the change, want to do a check with folks to see if anyone had a real concrete application where deterministic signing is actually a hard requirement, such that if we ripped it out, it would not break your use case. There's a lot of reasons to pull this out. The security concerns are perhaps paramount. And there are 2 open pull requests to basically propose a way to enact the proposed resolution that I just went through. One of which, I forget the number, and I should have included here, my apologies. One of which basically introduces an external API on top of the internal API, or on top of the existing API in the specification. And this external API would be the thing that's responsible for sampling local randomness and then equally, or also passing it to the verifier such that it can verify randomness plus message. And that's sort of the approach we're leaning towards right now. Minimally invasive with lots of text to talk about how applications should use this in a safe way. And I believe that's it. I don't think there's another slide. Okay, great.
Anybody have any feedback on this question for the RG?
I should note also that at this point, once we merge this resolution, the key binding draft, we're basically going to be done. We will have the security analysis and everything complete. So whatever's the next step at that point.
Yeah, I recommend getting some confirmation on the list with the link to the PR, if done. Okay, nobody's in the queue.
Thank you.
Move on to Bjorn. Thanks, Chris.
So, okay, sorry for the noise. I was too early just now. Can you hear me?
Yes, we can.
Okay. So I'd like to give you a short update regarding the case draft. Essentially, maybe next slide. Essentially, we have no content change in the current draft 6, which I've uploaded yesterday after the service got open again. If you go to the next slide. And basically, what we have been doing when changing from draft version 5 to 6 is that we modified the write-up. So it became clear in the discussions that we had on the list and off the list that we probably should focus on a clear set of readers and a clear set of audience. And as we have completed the security analysis of CPACE in the AsiaCrypt paper, which clearly covers the scope and the cipher suites that we are discussing in the draft, we decided to focus rather on the perspective of the application architecture designer, the implementer and tester for implementations of CPACE. So following the feedback that we got for the version 4 and 5 drafts, we rewrote the introduction completely and focused it on the implementers. And that's basically the change which we have applied, which covers the new draft version, which is online. And we would welcome a broader review and also maybe a review from a native English speaker regarding the draft. And the next step in our perspective would be a review from the crypto review panel board and other potential users and people that would be using CPACE. So that's, if you go to the next slide, that's essentially the message. I'd like to motivate you to have a look on the new write-up of the draft version 6. As next step. And essentially, from respect on the content, there's been no change.
Any quick comments? If not, thank you.
Okay, fine.
Right. The last two presentations are related to recent NIST results on PQC contest. So, hold on. Okay. Sophia, you can start.
Yes, thank you. So, hi, everyone. Today we're just giving a quick presentation with Tom Bbs about the post-quantum cryptography in its process. My name is Sophia Selly. Thank you for having us here. Next slide, please. Okay, so just to give you a little bit of a disclaimer / preface here, what we're going to be presenting is not a complete overview of the whole NIST process because that will take a really long time to do. But we just mainly summarizes the results of the first milestone that this process has actually reached. And there's some bias that you're going to hear from us, but we try to make the presentation as neutral as possible. And we also we're not pointing into actually choosing any specific direction, but rather treating this presentation as a conversation started. And if you want to learn more, our recommendation will be that you read the NIST report of the first milestone that they reach. Next slide, and now Tom, please.
Yeah, so if you saw the report or some stuff on Twitter, then you might have seen that Kyber is the chem that has been chosen for key exchange in a post-quantum way. And there are actually 3 signature schemes. We're going to provide a very, very brief overview here and basically just stealing this report and yeah, summarizing it very, very briefly. So if we go to the next slide, Kyber is the KEM, the key encapsulation mechanism that has been chosen. There are a few others that are still in the running that might be standardized later, but that will probably take a while still. Kyber is quite fast, quite efficient, and is based on lattices. Something which is important in the context of making protocols and putting this into stuff is that it's important to realize that chems are not the same as Diffie-Hellman. So while it has been applied in, for example, TLS very straightforwardly, because chems are interactive, you cannot put it, for example, into signal. Next slide, please.
Okay, all right. So Tom just talked about the key encapsulation mechanisms, which are basically the ones that NIST standardized in order to preserve confidentiality in the face of quantum computers. But NIST also decided to select certain algorithm for standardization to protect the authentication in the face of quantum computers. And those are the signature schemes. And the ones that were chosen were three. The first one is dilithium, which is very general purpose, and it's the main recommendation that NIST provides. But as you can see here on this slide, the sizes of the public key and the signature of the lithium is much more bigger when compared with the classical counterparts. On the bright side, though, the computation times of the lithium is much faster than the classical counterpart that we use nowadays. Next slide, please. The second signature algorithm that NIST recommends for the standardization, that NIST is going to standardize and is recommended to be used is Falcon, which sizes are indeed better if you compare them with the lithium and could indeed be used in certain protocols. The problem with this is that in order to instantiate Falcon, you have to use a floating point arithmetic, and that could be really cumbersome for certain implementations because the implementation have to be done very much correctly. So there's the assumption that you could use this scheme, but only if you are correctly implementing it. Next slide, please. And the last one, the last signature algorithm that was proposed that is going to be standardized is Sphinx, which is a stateless hash-based signature that maybe you already are a little bit familiar with because the CFRG has already standardized XMSS and LMS. But as you can see here, the algorithm has nice sizes for the public key, but not so much for the signature. And indeed, because it has a lot of hash function calls, it is pretty slow. And also, there are many parameter sets that essentially are going to be determined by NIST. But as it is currently right now, this is an algorithm that has a lot of parameter sets. And the reason why it was chosen is because the previous schemes, the lithium is based on lattice-based assumptions, and this one is based on a set of different assumptions, so it provides a wider range of security notions for the schemes. Next slide, please.
Yeah, so to briefly reflect on those current IETF standards, it's very important to realize that those are stateful hash-based signatures. So although they are quite a bit smaller than what Sphinx Plus is giving you, this state management issue. And if you, for example, restore your key from a backup, you're completely screwed. So that's why it's important to note that this is definitely a very significant difference. Falcon and the lithium are, of course, based on lattices and do not have state. Next slide, please. So I already briefly mentioned that there's a few more chems that are still in the race. If you read the report, it's more or less feels like NIST is either waiting for more research and waiting to mature certain schemes a bit more, and otherwise isn't exactly sure what to do. So McLeese, Bike, and HQC are all based on codes. Classic McLeese has a very tiny ciphertext, but public keys in the megabytes, so NIST isn't sure if that's actually useful. Tell them if you actually do like it. Psych is very fancy isogenes math, but it's very new, still quite slow, but actually very, very small compared to Kyber, so that is very nice. And Bike and HQC are sort of similar, but have slightly different trade-offs. You see that these schemes are all not lattices, which seems why, the main feature in these alternates. And then there's going to be some signatures as well, and that's what Sophia is going to tell you about in the next slide.
Yes, finally, as I said, the NIST process is not ended, but rather they reached the first milestone. One thing that they also announced is that, as Tom said, they're going to be still advancing certain algorithms for a fourth run. And they also are calling now for a next call of proposals specifically for digital signature algorithms. And the reason is because, as you saw, the majority of digital signature algorithms have like bigger sizes that maybe would be cumbersome when actually putting them into network or protocols. So this new round is going to come. There's already some hope of certain algorithms, like for example, Mayo, that seems very nice, but it still needs certain security checks to actually attest to the correct security of the algorithm. And of course, also to just let you know, don't expect any NIST standards before 2030, because at least the end of this next call of the process is going to take several years, as it did with the previous call. Next slide, please. Okay, if you are actually very interested and want to really start running code, there's already all of these libraries, specifically LibOQS is a really great library because it performs a lot of safety check of the post-quantum algorithms, and it has many bindings to different other programming languages. There's also PQClean and PQM4, specifically for embedded applications. Next slide, please.
This one I think should have been dropped, but yeah, so these are some of the questions that you might ask today, basically, or a problem. Can we go to the next slide? So here we have a collection of links, notably in this report that we blatantly plagiarize here, and also some other fun research papers, as well as some blog posts that have real-world measurements, and a nice talk from some colleagues of mine that explain Kyber for a more general audience if you're not very into lattices. These links are all in the slide deck, so that's where I suggest clicking them. Next slide. And that was it already. We were trying to keep this slightly short to enable asking lots of questions or perhaps start discussion. So I guess we'll be taking questions. And there's one comment I can make already, responding to the chat. The non-interactive versus interactive thing with the CANs is a very important issue. And it's important to realize right now that there's no solution for non-interactive post-quantum key exchange yet that we have a lot of confidence in. There is Seaside, which is not in the NIST standardization project and will probably not enter it right now. Seaside security is hotly contested, and although it's quite small, it's also very, 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 very slow. Even at the very aggressive parameter set that exists today. And there's some work that I've seen that suggests that if you want to go conservative with that scheme, you're looking at tens of seconds of operation times, which is not nice. But Seaside, yeah, it's very new. I don't think that will be standardized anytime soon. So it's looking that for now, we will not have non-interactive key exchange post-quantumly.
There was also one question regarding lattices attacks. Yeah, it is true that there has been some research about the matter, but no drawing conclusion. There has been not a clear conclusion about the matter, and so far, it seems that the security assumptions under which the specific lattice problems that are used by the quantum algorithms seem to be secure. But yes, perhaps something to watch in the future. You got them, sorry.
Yeah, so this is all, of course, the bare minimum schemes. So you need threshold or fancy stuff. I think there's a lot of research to be done there still. And I see Falcon being brought up. And I think it's important to emphasize that NIST explicitly wrote that the lithium is the primary candidate for signature schemes, because Falcon is very easy to mess up, which is also sort of evidenced by there's basically only one implementation of the scheme, which kind of is a testament to the fact that just implementing Falcon is a technical achievement. And indeed, NIST explicitly noted in its recommendation that if implemented correctly, which I think is quite telling.
We have a question from Scott Fleur.
This is Scott Fleur, Cisco Systems. One issue that you did not bring up is IPR concerns. Kyber, the NIST, the sole NIST Chem selection has plausible patents on it, and we don't know if those patents are valid until some judge makes a ruling, which will not happen quickly. NIST has some agreements with the various patent holders, but they have not published them, so we do not know if they will be acceptable to everybody. If that's not the case, it sounds like we need to actually have an alternative, most likely NTRU, even though it was not selected by NIST. Your comments?
Thank you for raising that. That's indeed true. And specifically on the NIST report announcing the selected algorithms for standardization, NIST does indeed know this, and I think they say that if the patents have not been resolved by the end of this year, they will be advancing NTRU instead of Kyber. So indeed, it has been addressed by NIST.
I don't know if we particularly want to necessarily wait till 2023. And also, resolving things to NIST satisfaction does not mean it's resolving things to everyone else's satisfaction.
We're both not lawyers, and as you said, a lot of the information isn't out there yet. I don't think I can speak for any company's lawyers, but I do kind of expect that the fact of the matter is going to be that the next FIP standard will require Kyber, whatever, if NIST does reach some agreement. I have no idea what that means for adoption, etc. I think it's a worthwhile discussion to have, especially as we reach more information. But I really can't say anything useful about that right now. This
Actually,
is what we've been given so far.
As far as NIST is concerned, you are perfectly NIST compatible if you're using, say, elliptic curve, P56, and some other mechanism such as NTRU. That is perfectly acceptable to them.
Yeah, for the moment, at least for the FIP certification, if you concatenate a classical algorithm with an experimental one for the key exchange part, I think it was FIPS 140, it's compatible. Yes. If that will change, I don't know. So maybe this is something that indeed could be started at a discussion, but I don't think we will get a lot of clarity also on the coming months. So my recommendation would be to kind of see where the different discussions are going around this.
Yeah. Personally, I'll be putting together a draft submission to the CFRG for an NTRU, so let's see if they can make that into an RFC as well, just in case the NIST approval process does not, patent process fails.
All right, last question from the room.
All right, was curious, you noted some of the difficulties with Falcon implementations, et cetera, and I'm working downstream on some of the post-quantum serializations, more at like the Jose side of things. Question about how should we be thinking about non-lattice-based stuff, because this was pretty clear that there's going to be steps down some of that paths. Are there 2 or 3 things we should be looking at early just to be aware of on the non-lattice-based approaches and prioritizing some investigations around?
I think I can comment on that. So a scheme that was out last month, but Rainbow is a refinement of UOV, and it's pretty, the way that the call for new signature schemes is written, it's pretty clear that they are basically calling for a UOV submission. So then you're looking at computationally, it's going to be somewhat okay for certain values of okay, but the public keys are going to be massive, 400 kilobytes, massive, but very small signatures on the other hand. So I think if you want to play with something right now, there's some code for Rainbow still out. I expect that UOV code will also be available soon. And there was already some discussion on the P2C forum, the NIST mailing list, about parameter sets for UOV. So you can get some idea of the sizes there. But I think that is the most significant thing that will, I would bet money on that will make it into the on-ramp for new signature schemes. There's some other stuff that we put in the slides, and that's much less certain if that's going to make it, because those kinds of schemes are much newer, and NIST did specify that they want mature cryptanalysis to exist of your scheme. And UOV itself, Rainbow was a variant of UOV, and the attack lies in that variant. I think that the confidence in UOV itself is quite high. So I think that will probably be accepted into this on-ramp thing.
Okay, thank you, Tom and Sophia. Last presentation of the meeting is going to be Bas Westervan.
Good morning. Can you hear me?
Yes.
Perfect. Thank you, Tom. Thank you, Sophia. Next slide, please. I think Tom and Sophia basically covered everything on this already. So Kyber is the post-quantum key agreement that NIST will standardize first. It would likely perform great. So that's very good news. Next slide, please. So it will take some time before NIST actually has it standardized. They just said that they will standardize it. We expect probably in 2024, but we never know. There are still changes likely to Kyber, but I expect many early adopters before 2024. Next slide, please. That's why we would like to have an RFC, a draft, but we want to match NIST's final standard. So what's the point then? Well, the drafts can be used as a reference for early adopters instead of everyone doing something different. A different advantage is that NIST will not include a machine-readable specification, and we intend to, in this case Python, but maybe something else. Also, it will have the IETF closer to the standardization, as the Kyber team is very eager to help out on this draft. And it will unlock early usage in, for instance, TLS, because code points are cheap. Next slide, please. So, any questions, concerns? Is there interest for this?
Philhan Baker, yeah, I'm very interested in this. I don't particularly care if it matches what NIST comes out at in the end, because what I'm concerned about at the moment is not doing PQC cryptography. I can't because I'm doing threshold, but I would like to be able to set myself up a safety net of shared secrets and roots of trust that are PQC hardened, so that if there is a quantum computer produced, I can then back out and recover my security context. I can do a new release that is secure, but I'm only looking to establish those shared secrets for a limited application. And the other thing you can do is that once I've got a shared secret, I can create a global mix-in that will PQC harden all my other stuff, like Russ Housley did in his draft.
Okay. Any other questions in the room? We have one online, and then we'll take the question in the room.
I think I'm online.
Oh, that's you. Okay.
Hi, I'm Flo from UK NCSC.
I just want to say it's really, really good to see this happening, kind of following on from NIST's announcement. I guess as a contrast to the earlier comment, I think it's really important that eventually we do match with NIST specifications. I appreciate all the reasons to start doing this work now, but I think in the end, it's critical that these match up and we don't end up with fragmentation between standards bodies. Thanks.
Okay, thanks. And I want to remind folks that the TLS meeting is later in the day. And I don't know if the TLS chairs have anything to share about opinions with respect to early definition of PQ algorithms for key exchange in CFRG, whether that's helpful or not. If you have anything to say, no, nothing to say at this time. Great. Okay, well, we are ending a little bit early despite the delay in the start. Folks did kind of push through these presentations pretty quickly, so thanks everyone for attending. And thank you, Rich, for taking notes. And we will have the notes up sometime soon. Thanks all for coming.
Yeah, I'll just surely try to catch up with data. Just yeah.
Yeah, and it's not a complex story though, right? There's so many sources to manage. It's really just reducing the feasibility of doing it from a cryptographic perspective. Reducing that kind of fixed IETF signature that can't verify, right? The trick is with actual face recognition, because you reveal a high IETF or something like that. So it's not the complex story. Yeah. No, yes. Yeah. So there's an extension to our key binding to a device. So be confident and say part of the verifying party. That's the